Section number 15 of the Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Eric Metzler, Albuquerque, USA. The Science History of the Universe, Volume 2, edited by Francis Rolt-Wheeler. Geology. Chapter 8. Vulcanism. Part 1. A volcano is usually a conical mountain or hill with an opening or crater through which various solid, molten, or gaseous materials are ejected. The essential part of the volcano is the opening or vent, and some volcanoes consist of almost nothing else. It is known that at least a part of the interior of the earth at a certain depth is hot, and a great part of it is actually or potentially molten. Thus a volcano might be considered as a connection between the interior and the surface, or as a chimney over an especially active part of the interior. The number of volcanoes now active may be estimated at about 328, of which rather more than one-third are situated in the continents and the remainder on islands. The active volcanoes are not scattered haphazard over the surface of the globe, but are arranged in belts or lines, which bear a definite relation to the great topographical features of the earth as well as to the seismic belts. Two of these belts together encircle the Pacific Ocean. A third band occupies a ridge in the eastern bed of the Atlantic, from Iceland to beyond St. Helena, from which arise numerous volcanic islands and submarine vents. The phenomena displayed by different volcanoes, or even by the same volcano at different times, vary greatly. It often seems difficult to believe that similar forces are involved, and that the divergences are due merely to different circumstances attending the outbreak. A careful comparison, however, of the varying phenomena brings to light a fundamental likeness in them all. Some vents, like Stromboli in the Mediterranean, are in an almost continual state of eruption of a quiet kind. Others, like Vesuvius, have long periods of dormancy, broken by eruptions of terrible violence. The first recorded eruption of Vesuvius, which occurred in 79 A.D. and is described in two letters written to Tacitus by the younger Pliny, was of the explosive type. In this frightful paroxysm little or no molten lava was ejected, but so enormous was the quantity of ashes that at Misenum, across the Bay of Naples, the sun was darkened, as Pliny reports, not as on a moonless, cloudy night, but as when the light is extinguished in a closed room. In order not to be covered by the falling ashes and crushed by their weight, it was necessary to rise often and shake them off. The explosive type of eruption is exhibited in its extreme form by several of the East Indian volcanoes, and preeminently by Krakatoa, the eruption of which in 1883 was the most frightful ever recorded. This volcanic island, situated in the Strait of Sunda, was little known, except that it had been in eruption in 1680. The catastrophe occurred in August, when, besides the fearful devastation caused by the disturbances of the sea on the coasts of Sumatra and Java, the island itself was almost annihilated. The force of the explosion produced waves in the atmosphere which were propagated around the whole earth, and the first one was observed in Berlin 10 hours after the explosion. The ejected materials were all fragmentary and of an incredible volume. Ashes were distributed over an area of 300,000 square miles, the greater part falling within a radius of 8 miles around the island. Stretches of water that had an average depth of 117 feet were so filled up as to be no longer navigable. Enormous masses of pumice floated upon the sea and stopped navigation except for powerful steamers. The flaming red sunsets which characterized the autumn and winter of 1883 to 1884 have been very generally ascribed to the refractive effects of the impalpably fine Krakatoa dust. The islands of St. Vincent and Martinique in the Lesser Antilles were devastated by a series of fearful and nearly simultaneous explosions, which in certain important respects differ from those of any other known volcanoes. The volcano of St. Vincent, known as La Soufriere, began breaking out on May 6, 1902, in a series of tremendous steam explosions. May 7, the eruption became continuous, and on the same day occurred the dreadful descending hot blast, a cloud of superheated steam and other gases, mingled with red-hot particles of ash, which rushed down the mountain and destroyed 1,400 human lives. The eruptions, which were repeated at varying intervals and with different degrees of violence for considerably more than a year, were characterized by the absence of lava and by the vast quantity of finely divided ash ejected by the explosions. The eruptions of Mont Pelée in Martinique were actually less violent, but far more destructive to life than those of St. Vincent. On May 2 the ejections of ash became frequent, increasing until the 8th, when a descending cloud of hot vapors and glowing ash swept with terrible velocity down the ravine of the Rivière Blanche upon the city of St. Pierre, which, together with its 30,000 inhabitants, was instantly annihilated. The velocity of the air set in motion by the descending cloud was sufficiently great to hurl from its pedestal the great iron statue of Notre Dame de la Garde, weighing several tons, to a distance of more than 40 feet. It is the descending clouds which lend such an exceptional character to the eruptions of St. Vincent and Martinique, but Mont Pelée also displayed certain other peculiar phenomena. While no lava streams were produced, very stiff and viscous lava appeared at the summit, filling up the old crater and forming a steep cone, through which protruded a lofty obelisk or spine, which, thrust up from below, grew irregularly in height, as it continually lost material by scaling off the top and sides. Eventually it fell altogether. In all eruptions of the explosive kind, a few typical examples of which are described above, the active agency is obviously exploding masses of intensely heated and compressed steam, and all such eruptions are accompanied by gigantic steam clouds, which, condensing in the atmosphere, fall in rains of torrential volume and violence. The hot water thus produced mingles with the volcanic ash in the air and on the ground, forming streams of hot mud, which are often more destructive than the lava flows themselves. When cold, the mud sets into quite a firm rock, called tuff. The opposite extreme of volcanic activity from the explosive type is to be found in the volcanoes of the Sandwich Islands, such as Mauna Loa and Kilauea. Here the eruptions are usually not heralded by earthquakes. The lava is remarkably fluid and simply wells up over the sides of the crater, pouring down the sides of the mountain in streams which flow for many miles. More commonly the walls of the crater are unable to withstand the enormous pressure of the lava column, and the molten mass breaks through at some level below the crater, rising through the fissure in giant fountains, sometimes 1,000 feet high. Even in the ordinary activity of Kilauea, jets of 30 and 40 feet in height are thrown up. Hardly any ashes or other fragmental products are formed, and though the clouds of steam, the invariable accompaniments of volcanic outbursts, are present, yet the quantity of steam is relatively less than in those volcanoes in which explosions occur. Between such extremes as the Hawaiian volcanoes on the one hand and the explosive East Indian type, Krakatoa, on the other, may be found every intermediate gradation. Thus, though occasionally breaking out with violence, Stromboli has been in a state of almost continuous activity for more than 2,000 years, and is for long periods in such exact equilibrium that barometric changes have a marked effect upon its activity, and the Mediterranean sailors make use of it as a weather signal. Evidently one active agent in these phenomena is imprisoned steam in its struggles to escape. Different as are the manifestations at various volcanoes, steam is an important cause of the eruption in all cases, though the conditions under which it acts vary widely. In the modern eruptions of Vesuvius essentially the same phenomena may be observed, but on a far grander and more terrible scale. Earthquakes usually announce the coming eruption, increasing in force until the outbreak occurs. Terrific explosions blow out fragments of all sizes, from great blocks to the finest and most impalpable dust. Inconceivable quantities of steam are given off with a loud roar, which is awe-inspiring in its great and steady volume. A volcano, as its activity wanes, may pass into the solfataric stage, when only volatile emanations are discharged. The well-known Solfatara near Naples, since its last eruption in 1198, has constantly discharged steam and sulphurous vapors. The island of Volcano has now passed also into this phase, though giving vent to occasional explosions. As the result of solfataric action, masses of rock are decomposed below the surface and new deposits of alum, sulfur, sulfides of iron and copper, and layers of silica, etc., are formed above them. The lagoons of Tuscany are basins into which the waters from soffioni are discharged, and where a precipitation of the dissolved salts takes place. Among the substances thus deposited are gypsum, sulfur, silica, and various alkaline salts, but the most important is boracic acid, the extraction of which constitutes a thriving industry. Another class of gaseous emanations betokens a condition of volcanic activity further advanced toward final extinction. In these the gas is carbon dioxide, either issuing directly from the rock or bubbling up with water which is often quite cold. The famous Valley of Death in Java contains one of the most remarkable gas springs in the world. It is a deep, bosky hollow, from one small space on the bottom of which carbon dioxide issues so copiously as to form the lower stratum of the atmosphere. Tigers, deer, and wild boar, enticed by the shelter of the spot, descend and are speedily suffocated. Many skeletons, including those of man himself, have been observed. Death Gulch is the significant name to another example of the accumulation of carbonic acid in Western America. Eruptive fountains of hot water and steam, to which the general name of geysers, i.e. gushers, is given, from the examples in Iceland, which were the first to be seen and described, mark a declining phase of volcanic activity. Iceland has long been famous for its geysers, and a very beautiful series in New Zealand was destroyed by the volcanic eruption in 1886. But probably the most striking and numerous assemblage is that which has been brought to light in the Yellowstone National Park. In this singular region the ground in certain tracts is honeycombed with passages which communicate with the surface by hundreds of openings, whence boiling water and steam are emitted. In most cases the water remains clear, tranquil, and of a deep green-blue tint, though many of the otherwise quiet pools are marked by patches of rapid ebullition. These pools lie on mounds or sheets of sinter and are usually edged round with a raised rim of the same substance, often beautifully fretted and streaked with brilliant colors. The eruptive openings usually appear on small, low, conical elevations of sinter, from each of which one or more tubular projections rise. It is from these irregular tube-like excrescences that the eruptions take place. The term geyser is restricted to active openings whence columns of hot water and steam are from time to time ejected. The non-eruptive pools are only hot springs. In the upper Firehole Basin of the Yellowstone Park, one of the geysers, named Old Faithful, ever since the discovery of the region, has sent out a column of mingled water and steam every 63 minutes or thereabouts. The column rushes up with a loud roar to a height of more than 100 feet, the whole eruption not occupying more than about 5 or 6 minutes. The other geysers of the same district are more capricious in their movements, and some of them more stupendous in the volume of their discharge. The eruptions of the Castle, Giant, and Beehive vents are marvelously impressive. The action of geysers is due to the conditions that subterranean waters have access to hot rocks, as the interior of great lava sheets, retaining a high temperature on account of the poor conductivity of the material, and that the conduit communicating with the surface is so narrow that convection currents cannot be freely established. The heat accordingly increases in the deeper part of the column of water until steam is formed, by whose expansion the cooler waters above are explosively ejected. After an eruption the water flows back into the underground passages and gradually becomes heated up for another explosion. Heated waters act on the rocks with which they are in contact and decompose them, and, as most rocks, especially volcanic rocks, contain some kind of feldspar, the waters become slightly alkaline through the alkali of the feldspar, and so are enabled to take up silica and make siliceous solutions. The silica taken into solution is deposited again around the geyser in many beautiful forms and makes the bowl or crater from which the waters are thrown out. From a geological point of view, the products of volcanic action form a most important part of the subject, because they contribute largely to the permanent materials of the earth's crust. Volcanic products are of three kinds: 1. Lava or molten rock; 2. Fragmental material, including blocks, lapilli, bombs, the so-called volcanic ashes, cinders, and the like; and 3. Gases and vapors. A lava is a more or less completely melted rock. The degree of fluidity varies greatly in different lavas, but is rarely if ever perfect. The degree of fluidity depends upon several factors, the most obvious of which is temperature. The more highly heated the mass is, the more perfectly will it be melted. The quantity of imprisoned gases and vapors present has also an important effect, and some lavas appear to owe nearly all their mobility to these vapors. A third and most significant factor is the chemical composition. Those lavas which contain high percentages of silica, the acid lavas, are much less readily fusible than the basic lavas, in which the percentage of silica is lower. When a lava stream reaches the surface of the ground, the imprisoned vapors immediately begin to escape and the surface of the molten mass to cool and harden. The surface layers are blown by the steam bubbles into a light, frothy or slaggy consistency, forming scoriae, or cindery masses. The motion of the lava breaks up this thin crust into loose slabs and blocks, and on the advancing front of the stream these loose masses rattle down over one another in the wildest confusion. The front of a lava stream advances, not by gliding over the ground, but by rolling, the bottom being retarded by the friction of the ground and the top moving faster, so that it is constantly rolling down at the curved front end and forming the bottom. Ordinarily the motion soon becomes very slow, though thoroughly melted masses pouring down steep slopes may, for a short time, move very swiftly. One of the lava floods from Mauna Loa moved 15 miles in 2 hours, and for shorter distances much higher rates of speed have been observed, but this is very exceptional. When lava cools rapidly, it solidifies as a glass, obsidian, or tachylite. When it cools slowly, it forms a truly crystalline rock. Between the extremes are various gradations. If the swiftly cooling portions have been much disturbed by the bubbles of steam and vapors, they are made light and frothy. In some cases, as in pumice, they will float upon water. The lavas which contain large crystals embedded in a finy stone or glassy base are said to be of porphyritic texture. A mass of lava, when it cools and solidifies, necessarily contracts, and since the cohesion of the mass is insufficient to allow it to contract as a whole, it must crack into blocks, separated by fine crevices, which are called joints. Not all the lava produced in and around a volcanic vent can reach the surface. Some of it may be forced horizontally between beds of the surrounding rocks, thus forming intrusive sheets, which, when exposed in sections, may be readily distinguished from surface flows by the fact that they have consolidated under pressure, and hence have no slag or scoriae associated with them. Other portions of the lava will fill up vertical fissures in the volcanic cone or in the underlying rocks and, solidifying in these fissures, form dikes. Such a fissure, 12 miles in length and filled with molten lava, was observed by Sir Charles Lyell in the neighborhood of Etna. End of section 15. Recording by Eric Metzler, Albuquerque, USA. January 2016.